Storage isn't just a battery, and it's not just a hot water heater that can change its timing. It's a whole lot of different things. It's assets that can respond to power grids and change the way they perform. And just by way of background, my name is Kelly-Detwiler. I used to work at Constellation Energy and headed up the demand response group, and I've been in power for 25 years. Currently, I write for Forbes.com, and I've interviewed and written articles, about 200 articles over the last 2.5 years. And I've had a chance to interview a number of the people on this panel about their business models. And I have a chance to look at solar, storage, wind, what's going on Marcellus Shale, and everything that's going on in power grids. And so every time I see somebody like, Senator Imhoff throwing a snowball on the floor of the Senate saying climate change isn't real, I can tell you what I think about that. There's science, and then there's people who don't really think about the scientific method or have confidence in it. Every time something like that gets me down, I think about folks like these 5 people here and the solutions they're creating for the power grid and how we're getting smarter about how we use energy and how much faster we're learning, how much more quickly our simulations are for wind blades or new ways of building towers or improving the efficiencies of solar panels, or indeed, how do we store power and create a more interactive, dynamic, efficient, economically efficient power grid for the future. For us in our waning years, mine are closer than some of yours, and for our kids. How do we make this actually into a sustainable power grid? Storage, in all of its different forms, is a critical piece of that, especially as we get more renewables in place. The sun doesn't shine 24/7, and the wind don't blow 24/7. Nor does the tide move that way or anything else. So, having the ability to store means we can do a lot more things with our power grid and make it more efficient. So today, we have a panel full of experts. So who we have here today, we've got Ron Van Dell, who is the CEO of VIZN. Most battery companies are located in California where it's nice and sunny, and I don't know why Ron ended up in Montana. He'll have to tell you about that. And then we've got Leigh, and she works in business development at Greensmith. Greensmith is a company that looks at markets and takes these storage media and optimizes what they do. And it's a really cool company. Their founder and CEO, Jung, is really charismatic. He's got a great team. Lisa's one of them. She can talk all about different aspects of this thing, and we hope to get her to today. Then we have Ryan O'Keefe, and he's with Ideal Power. And Ideal basically deals with inverters, converting power from these assets, batteries, solar, et cetera, from DC into AC so the grid can consume it. And he's got a unique technology. We're going to talk about that. Then we have LocalGrid Technologies, Bob Leigh, President and CEO. And Bob deals with the customer side of things on the fringe. How do assets that consume power talk to the grid and optimize what they're doing? How do we make that conversation so that it's not a Tower of Babel? And what we're going to see in years to come is, as we get from petascale into exascale supercomputing and more data being stored and all these sensors telling the grid what they're doing, we're going to see more automated demand response, more storage that's automated, more communication within the power grid. It's going to be a huge software and IT play. How do you get those all to talk to each other? That's what Bob's going to talk about. And then finally, on the generation side, we've got these generators out there, and some of them have efficiency issues, and one of them, natural gas-fired plants. We see more and more of those every day. We see gas displacing coal, and most of the new fossil fire generation that's being added onto the grid right now, it's certainly not coal, it's natural gas. Because gas is cheap, you can build the plants within a few years, and the permitting issues aren't nearly as difficult as nuclear or coal. So the technology we have from Tom Pierson's company, TAS, basically improves the efficiencies of natural gas-fired generation through a storage technology, and we'll talk about that. So what we're going to do, now that I've stolen all their thunder, is have each one of our participants introduce themselves and their company for about 3 minutes. So about 15 minutes into the conversation, then I'll ask them some leading questions to try and tease out more of the story, and then as quickly as it makes sense, which will probably be pretty quick because I'll exhaust my intelligence in no time. This battery's got limited life. We'll then turn it over to you all in the audience and crowdsource the intelligence that way. We hope to make this a very lively discussion to engage all of you. And without further ado then, Ron, if you can take it away.
Sure. Thank you. Is this
Actually,
working?
keep this.
Okay. So for the fraction of you who weren't here for the last half hour, some of this will be a little bit of a repeat, but without trying to say anything obvious to this audience, we see there being a couple of pretty big drivers for storage, one in the developed world and one in the developing world. They're completely different, but they still drive storage that I think to one degree or another we'll all be involved with. In the developed world, as Peter just talked about, certainly renewables integration combined with decreasing grid headroom is a need for a shock absorber that the grid doesn't have right now. But I think one that also doesn't get talked about enough, and I'll fit it into my 3 minutes here, is the developing world, where you've got somewhere between 1.3 and 1.4 billion people on the planet who have no electricity at all. They are not going to get electricity with a large centralized coal-fired plant and transmission lines and substations down to a conventional distribution network. They're going to get a couple of wind turbines, maybe some solar panels, a few of the right kind of batteries, and they're going to basically go one village at a time. And that's how you're going to ultimately bring electricity to those people and everything that implies. So as a company, what we do is a flow battery. It's a zinc iron flow battery. There's such applications diversity out there. This is such a complex opportunity, but also a huge market. There isn't going to be one right answer, as I'm sure we'll get into again. But what we do is a flow battery that has both power and energy capabilities, that has inherently very, very low cost and is intrinsically safe. It's non-toxic, non-flammable, and non-explosive. And that trifecta of elements together is just really freaking hard to do. And that's what we're all about. And I'll pass it up.
Excellent. I'm with Greensmith, and Greensmith was founded about 6 years ago by two gentlemen who came from the cloud computing and data storage world. And what they realized is that a lot of the concepts and challenges that you get in cloud computing are directly relatable to energy. If you think about it, cloud computing is really a supply chain issue, right? How do you balance supply and demand? How do you make sure that the inventory that you need, whether it's data or electrons, is in the right place at the right time for the people who need it the most? And so a lot of the lessons that were learned in that realm were transferred over to looking at how do you have a vision for energy into the future, which is distributed, which is bidirectional, and that allows you to make the most efficient use of the assets that are located at various points within the grid, again, whether that's the data grid or the electrical grid. So what Greensmith does is we are the control layer. Today we control the assets that go into a single site, and that's the batteries, the inverters, the converters, the balance of plant, all the things that go into having a grid-scale energy storage system. These are megawatt-plus systems. We also do turnkey solutions, so in the process of developing expertise on the technology side, we develop a lot of expertise on how to design and build and deploy systems, and so that's a lot of what we do. And as I mentioned earlier, Green Tech Media came out with an analysis a couple of weeks ago that said that about 62 megawatts of storage went into the US in 2014, and we were responsible for about 25 megawatts of that. So over a third of the storage that went into the ground in the US last year was Greensmith deployed and is managed on an ongoing basis by our software.
Thanks, Lisa. Okay, for those of you that were here earlier, I apologize for my analogies. You're going to hear them again. So the energy storage, battery energy storage space is kind of like a three-legged stool, right? You have the battery itself, which is the frame and the engine of the car. You have the system integrator and control software, which is kind of like the driver's cockpit, the steering wheel, the gas pedal. And then you have the power conversion system, or the inverter, as many of you call it. And we're kind of like the transmission. It's a really important part of the system. You absolutely need it for the vehicle to function. Nobody really wants to talk about us, and you don't really realize you need it, or that you use it until you have a problem and it breaks and it's very expensive. But that's not to say power inverters, power converters are a critical part of the energy storage system. The utility world we live in is an AC world, and PV panels and batteries are DC. So to get energy storage and to get renewables to work with the grid, you need to be able to efficiently and effectively convert that power back and forth from DC to AC. Ideal Power is based here in Austin. We are a power converter technology company. We focus on what's inside the box, and we've invented really a revolutionary new way to do power conversion. It's a mechanical software solution. We call it power packet switching. It's smaller, more efficient, and eliminates a lot of the bulk magnetics and capacitive components. So I'm happy to talk to you all more about that later through the questions. We just say that the energy storage is sort of been called the Holy Grail, which is the topic of this session, or the missing link. But what it is, it's really a transformative element as you look at how renewables are going to sort of grow on the grid and how the grid economy is going to transform from the traditional utility model to the distributed model. Energy storage is going to play a key part, and that's what we hope to talk a lot more about in this panel. Thanks.
Thanks. Bob Leigh with LocalGrid, and we're an embedded software company, so whereas most of the people here are about storage and stacking up that value chain, we look across a broader selection of assets. And our mandate, our reason for being and the value that we provide to the industry is how do you connect all these different assets into existing infrastructure with the utility, with each other, so that you can drive more value from them, and as well as with other legacy systems that already exist in the field. So it's a big challenge when the utility looks at it. It's a big challenge when some of our customers look at it. We've got all these different protocols, all these different systems. We know there's value there. We've got all this data. How do we make sense of it? How do we bring it into some rational model? And our fog computing platform is about solving that at the edge. So not cloud computing. We're not providing back-end analytics. We're doing applications right at the edge, where at the location that the storage is installed, where the PV is installed, where the other control systems installed, EV chargers, solar carports, where you have a volt bar or controllers. How do we connect all of those systems together and aggregate that data and provide a platform to develop those applications as the utility evolves and the industry evolves? Our analogy is, if you look at your smartphone, especially your Google-based smartphones, you have a Linux operating system underneath. You have an Android layer on top of that, and a number of applications. We're the Android layer connecting all these hardware bits together and allowing applications to exist with each other and communicate with each other.
I'm Tom Pierson. I'm the founder of TAS Energy, and so we're a leading provider of generation storage. So if you're not familiar with that concept, generation storage is really an ideal fit where you need to store large amounts, like lots of megawatt hours a day. So for us, a typical project would generate somewhere on the order of 50 to 100 megawatts for 8 to 12 hours a day. So it's, you can do 1,000 megawatt hours at a single installation. Well, what's unique about this is it works alongside generation, not all generation, just gas-fired generation, gas turbines. So if you look at the renewable market, really, I think most people would agree that gas turbines provide the bridge, the cyclical firm capacity in large megawatt bulk that you need in order to firm up solar and wind. And gas turbines are a great asset. The only challenge for them is that they lose output when the weather gets hot. They go down about 1% of their nameplate capacity for every 2.5 degree drop in temperature, or increase in temperature, I should say. So when it gets hot, the air is less dense, and because it's like a big fan, the mass flow through the turbine gets less and less as the weather gets hot. That's why airplanes take off and fly a lot better in cold air than hot air. So the way generation storage works is you simply utilize low cost or off-peak power. In order to store power, you have to convert it into something. Batteries do it with chemicals. Other folks use pressure. We use temperature. So we convert the electric off-peak power to chilling, which is a very relatively easy, no technology risk there. and then store the chilling in a big tank. So for a 100 megawatt generation storage project, you might have something like about a 5 million gallon thermal storage tank. So you store the electricity as chilled water, and then when you want to regenerate it, you pull the water out of the tank and cool the air to whatever temperature you want. And you can selectively change that temperature because actually this is the most efficient way to adjust the output of a gas turbine rather than closing inlet guide vanes or duct firing or any of the ways that they modulate the output of a gas turbine. What you really should do first is adjust the temperature. And in the past, they didn't do that. They didn't have control of it. Whatever the weather was, it was. But now you've got the ability to precisely dial in anywhere from 50 degrees to 100 degrees or whatever using this stored thermal energy.
Thank you. So we can see that storage is not storage is not storage. It looks completely different to different people and for different uses. One of the questions that continues to intrigue me and I think many people is, how do you talk to all these assets? And one of the things that I find interesting about your company, Bob, is that you're dealing with end-use assets and people out on the edge and treating those assets and making them responsive so that they become storage as well. But there's a communications challenge there, isn't there?
Yeah, I mean that's one of the the big issues if you talk about the IT-OT convergence is how do you take all these operational assets and start to treat them like you would an IT asset, where they have flexibility and they can do more than one thing. So, one of the things that a lot of people talk about is virtualization of the devices, and that's one of the things that we're all about. Is you've got equipment out there, and storage is a great example. You've got many different applications for that storage, and it gets really nuanced when you combine that with other control systems. How do I use that storage not to maybe balance the grid, but balance my home, or balance what's happening at the substation? And so you're talking about connecting of a lot of different assets, and then you talk about smart cities, and you bring transportation into this, and you have different systems, different industries butting up against each other, and there's literally dozens to hundreds of different communication technologies, and then there's the system models and data models and everything else that goes along with that. So not to say that we've solved that problem, but we're working towards solutions that make it easier anyway. And it's and for us, it's about protocol conversion at the edge. So as soon as you take that asset and bring it into the network you want to support these applications, you translate it to a common model and a common system, and you want to support essentially legacy infrastructure that's already out there. So you want to be able to support old protocols, and you want to support the new protocols that are coming out. But at the end of the day, it's all about rationalizing that data and managing that data, because all of the applications really depend on data. So what is your objective in bringing all these systems? Well, it's to take that data and rationalize it and provide it to the cloud so you can make decisions at cloud, or it's to put an application out at the edge to convert that information to some useful action. Maybe it's changing your volt bar control scheme. Maybe it's managing your microgrid, which will include storage and renewables and everything else.
So who buys that from you? Who's the consumer who's willing to pay for your solution?
Right. So there's really three types of customers for us. One is some of really only the most progressive utilities that are trying to put these assets in the grid, and they have existing OMS, EMS, and SCADA systems, and they're not going to tear those down, especially for a pilot project. But they just won't accept. They won't accept renewable energy in the way that they won't accept the information that renewable energy provides. So one of our first customers with Toronto Hydro, they did, and they actually still do with the systems that we're not connecting to, they have a separate independent web interface to look at the renewables. It's not integrated with SCADA because their SCADA system is 5 years old, and they're not going to spend millions of dollars to upgrade their SCADA system for a few hundred megawatts of solar that doesn't have a big impact on their bottom line. So how do you get that system into their infrastructure? So it's about taking that data, doing some pre-processing on it, again, out in the field on intelligent switches on the edge of the network, so that then we provide the information in a format that the existing infrastructure can use. Other two categories are OEMs that are developing solutions, so they could be battery manufacturers, they could be microgrid integration companies, they could be other technologies, and we can get them to market faster by providing some of that data management, device management, and protocol conversion infrastructure. And then I'd throw systems integrators in there as well, where we can just provide a technology that gets them to their solution faster.
Thank you. So, Tom, you were describing how by virtue of alchemy, you can take off-peak hours, create chilled water, and conjure up more kilowatt hours almost from nowhere, except you burn more gas to do it. Who buys that from you? What does a typical customer look like, and what's that conversation sound like?
Well, first of all, it's almost always a power plant owner,
Mm-hmm.
because you have to have a power plant for this to work, a gas turbine-based power plant. Generally, it's a combined cycle. It's your more efficient assets. It'll work with simple cycle, but you would generally want to put this on your best assets, right? Because you get the same percent output, but at a better, a combined cycle heat rate. So for us, really, it's more of a function of the market. I mean, the technology works everywhere, right? But the markets are so different. So PJM is an example of a market right now I would say is the best in the United States for us. Even though it's not all that hot compared to other places, you probably don't get as many megawatts there as you would in Texas or even some of the places in California. But they have a capacity market, right? That's huge. The biggest challenge for our customers is how are they going to get paid for this? This is a huge problem in California. If you have a gas turbine asset and you want to add another 50 megawatts to your existing plant, you can't get paid for that. They'll just assume, well, this offtake, I'm already getting that, right? So there's no way to get repaid for the investment. So that's a challenge. In ERCOT, here in Texas, I think this is a relatively free market, but we're energy only, right? So, and I think a lot of folks were waiting to see if we were going to get a capacity market, which makes the financing of the plant much more assured. Otherwise, you have to, what does your crystal ball say? What is the value of power on August in 2027 when it's 105 degrees out? And, if your crystal ball says, well, that's a whole lot of megawatt hours, then you can justify it. But it's a much more difficult calculation, as you can set. Whereas PJM, if it's a fixed capacity market, and I know I'm going to get an extra 100 megawatts times that capacity, well, okay, I can bank that, right? It makes it a lot easier to finance the plant.
Great, thank you. So we're dealing with the former Yugoslavia here, right, with a lot of complex markets and different rules. Now, Lisa's looking at the former Yugoslavia on the market side, and she's dealing with a lot of different assets, different types of battery chemistries and so on. What does that look like to you, Lisa, when you're looking at markets and trying to figure out where and how to create value? How do you build that heat map, and what kind of conversations take place internally and with your customers?
Sure, yeah. I mean, I think we've all heard the cocktail party story about, how if Alexander Graham Bell came back to life today, he would find the telecommunications landscape unrecognizable, right? There's internet, Wi-Fi, mobile phones. Whereas if Thomas Edison came back to life today, he could go down to the local utility and get a job, right? I mean, and it's not even being facetious. I mean, it's probably pretty true. That's the kind of world that we deal with. From the technology point of view, our technology and our platform is I would by no means would say it's mature, but it's in its 4th generation, and it can do a lot of what needs to be done. It's a rules-based engine. It's a decision engine that can integrate lots of different assets, lots of different components, and do what needs to be done. Our challenge, to your point earlier, is it's waiting for the markets to catch up, right? It's this huge, sophisticated, very, very established grid that has been around for decades, over a century, that is not really used to change that happens on the scale that we're seeing today with the amount of renewables and the other sorts of changes happening at a very rapid rate. And so it's really those two forces coming together and us trying to look at what markets are most progressive, that are seeing what's happening down the road and are putting in the structures, the market mechanics, and the market mechanisms and the pricing signals that we can make storage work. Everyone focuses on the battery prices and all of that, and of course that's a huge part of making the economics work. But if you're not seeing the market exist for your technology, then that's the biggest challenge that we experience today.
Thanks. So Ryan, you're connecting all these assets to the grid, whether it's PV panels or batteries and so on. As you look out in the market, where are the soft targets to you, where do you naturally migrate and see your business opportunities, and which ones with limited resources do you stay away from, and why?
Sure. So we tend to be most effective at connecting battery systems to the grid because of the properties of our technology. So we're a commercial industrial size company. We focus on the commercial industrial markets. And there are absolutely economic opportunities today for commercial industrial users to monetize energy storage. Our biggest market by far in the C&I space is in California and New York. It's the demand charge reduction opportunity. So a typical commercial industrial customer, unlike a residence, pays not only for the kilowatt hours of energy they use, but they pay this availability fee, if you will, for the utility to have available kilowatt hours to them. And that fee is set by the peak usage they have in a given day of a month. So one really bad day with a lot of power, and you pay this fairly large fee. In some places, it could be almost 50% of the bill, called a demand charge. And in California, New York, Boston, a few other markets, Hawaii for sure, these demand charges are easily manageable through behind-the-meter energy storage system. My company is sort of the leader today in power conversion technology for those behind-the-meter systems. We don't make the systems, we just make the inverters. But that's a market that you can monetize today. And really, we're seeing 2, 3, 4-year paybacks in that market, depending on which state you're in and which rate you pay within that state for those systems. So that's low-hanging fruit. Moving up from there, you then have PV integrated storage. So a rooftop solar system at a business certainly reduces the kilowatt hours the business is using, but the problem is it's unpredictable. So, there is great sun in California, there's great sun here in Texas, but we still have cloudy days. And so when you have those cloudy days, not only do you pay peak consumption rates, but again, that demand charge creeps back in. So you can manage both the demand charge and your consumption by having a PV integrated storage system that can sort of set the ceiling of what you're going to consume or use.
Thanks. That is a perfect segue to Ron, because Ron and I just had a conversation a couple weeks ago about what VIZN's done in terms of lining up third-party capital to integrate solar storage combo opportunity to the marketplace, among other things. Ron, can you talk about A, that solar storage piece, and then B, the importance of third-party financing in moving? We've seen in solar, for example, in 2013, it was $3.34 billion worth of third-party financing, which is 80% of California's installed PV. And last year was $4.1 billion, and now we see storage starting to move in the same direction, lining up that money. What does that look like to you in terms of the long-term trends?
Yeah, I think there's a lot to be said for what was created over the last several years as a global food chain for solar is now becoming a global food chain for solar plus storage. Clearly, two things drove PV past a tipping point. One was China building twice as much capacity as the world would ever need, and what that did to ultimately competitive dynamics and pricing at a street level. So it became very, very rapidly more economical to buy solar panels. And then once that was combined with some pretty creative financing solutions, at least in the U.S., then I think you started to see a huge change in the adoption of solar. The U.S. went from kind of almost last place to the huge growth that we've seen in the last several years. What you're seeing now in storage is that the same EPCs, systems integrators, and financing institutions that have been riding that wave in solar now want to do the same thing with adding on the storage content, either because they just want to add on content, and it's in everybody's interest to do that, even for existing PV installations, or they're being mandated to go add storage because the renewable penetration is high enough that the parent grid operator is insisting on better behaved renewables than what was out there before. So clearly the opportunity, and this focuses again on, I think, the C&I market in some cases where we've partnered with LFC Capital to basically do very simple lease financing under $5 million per project, and combine that with a very simple product offering so that somebody who maybe doesn't want to deal with all the custom engineering and all the complexity of a larger scale system, say on a full-blown PPA, can still go do solar plus storage. So that's a big driver for adoption. In some ways, it's also a risk reduction for early adopters because you're kind of living with your own gear, right? And they feel better about that. I think another example of what's happening in the industry is, in addition to PJM and a focus on the regulation market and demand charge avoidance in California and New York, is you have a lot of places around the world outside the U.S. where the only way they get power are diesel gensets, right? It's convoys of diesel fuel going through the jungles of Africa or into India or into northern places in Canada where they only have roads, half a year. And that's somewhere between 40 and 80 cents a kilowatt hour. That's a pretty nice price umbrella to go in and say, well, what about renewables plus storage? Maybe keep the diesel gensets around to back up the battery, but maybe that's it. And people are seeing IRRs in the high teens to mid-20s% by doing that. So it's a very good payback. It's the kind of thing that larger scale financial investors who want to do a whole string of projects like this enabled by a certain technology can get behind on a global basis, and it doesn't depend on PUCs and regulatory kind of harmonizations in the U.S. So financing is a big reduction of barriers for early adoption, and I think outside the U.S., ultimately you're going to be looking at offsetting diesel gensets with a combination of renewables plus storage as demand drivers.
Thank you, Ron. So somebody had slipped me this little note that said finish by 3:30. And we've got 3:19 right now. So what I'd like to do for the next 10 minutes or so is open up questions to the audience so we can orient this towards your specific concerns and issues. Right there, sir.
Question for Mr. Pierson. In round numbers, what percentage increase can your technology, can your equipment boost the natural gas generators? And also, I'm having never seen the configuration, I'm having a hard time conceptualizing how you expose air to thermal storage. Is this just like a giant air conditioner duct? Okay.
And the percentage was what, roughly 10%?
Yeah, well, the hotter it is, the higher the percentage, right? So, like I said, every 2.5 degrees you cool the air, you gain 1%. So if it's a 100-degree day out, and we take it down to 50, you'll pick up about 20 plus % of whatever the output of that gas turbine was. So if it's a 1,000 megawatt power plant, now a lot of these would already have evaporative cooling, right? So even on a 100-degree day, evaporative cooling where you just dribble water into the air. Even on a 100-degree day, they may be able to get the air down to, call it 76 or 77. A lot of plants have that because it's real low tech and very low cost. So a 100-degree day, but the gas turbine sees 76 degrees. So we would take that 76 all the way down to 50, right? So in that case, more realistically, the output on a combined cycle plant as compared to evaporative cooling would probably be more like 15%, okay?
Scott Henneberry from Schneider Electric. This is just a conceptual question since we're talking about the Holy Grail, and anyone can answer this that chooses to. Will we achieve Holy Grail status with existing technologies, just scaling them and improving them, or do we need something new?
I'm going to take just a quick first stab at that. I guess that depends on if you're talking about just traditional storage or other storage, because I think a lot of technology exists to drive value out of existing loads, existing capacity, and treat that as storage. But I'm going to let someone else answer this storage-specific question.
Well, I think it's a very good question. I guess it depends on what you call existing technology. I mean, existing technology could go all the way from a lead-acid battery to what people are trying to do with lithium-ion batteries today, to a dozen, at least, startups that are trying to do better than lead-acid and lithium-ion batteries. I think if you look at lithium-ion and lead-acid as the incumbents, I think there are some limitations to how far they're going to be able to be improved and extended to actually fit the real usage cases that you see in a lot of different needs in energy storage. As we talked about a little bit earlier, some technologies are very good at one thing, but what you're going to need on a grid is an asset that can actually do a bunch of different things, because you aren't going to know which ones you're going to need 12 years into the life of a 20-year multi-megawatt deployment. So versatility and option value, we think, is going to be pretty important as well. The other thing that a lot of people don't talk about, and it's actually a little bit like the gas turbine example, whereas temperatures get higher, efficiencies can go down, is you do have a certain nexus between the technologies that have better energy density, which could be very important for electric vehicles, for example, and the close cousin to energy density, which is thermal instability. And there's a reason hydrogen and lithium and all of them are where they are in the periodic table, right? You can get a lot of power out of a small space, but that can sometimes lead to things that you wouldn't want going on, particularly in large storage assets that are deployed in communities. And so one of the things that made me think of it in talking about temperatures and gas turbines is, as things get hotter, which frankly is where you're going to see a lot of sunshine and a lot of need for doing things, particularly with solar, you're going to see more money have to be spent, more efficiency have to get used on keeping certain storage technologies within a certain temperature band that is consistent with them staying well behaved. Other storage technologies, for instance, in flow battery technology like ours, all we care about is the average temperature through the whole 24-hour period. So we can get really, really hot during the day, and as long as it's going to be cold at night, it's thousands of gallons of water, essentially. It's like, how hard or easy is it to raise and lower the temperature in your pool in your backyard? And so that inherent thermal stability starts to play into economics and to play into operating life when you're deploying these assets into areas that in themselves can have very high peak temperatures in the afternoon. So I think it does become nuanced, it becomes complicated, but ultimately, when you look at stationary, large-scale stationary storage applications, there's just a bunch of costs you have to add to those. To get to a complete ESS, you've got to put a lot of cost into that system on top of, for example, the lithium cell before you're done. And those costs get higher and those efficiencies get lower the more you operate it at elevated temperatures. So that's one of the reasons, one of several reasons why I just think you're going to see some of the need for some newer technologies to become more mainstream in the future.
Can I just add one quick thing, which is a vote for both software and design. So in the context of what we have today, without having to wait for that sort of quantum leap, you can do a lot in terms of how you operate the system. So computing power is very cheap. Battery power is still relatively expensive. So how do you use software to more efficiently eke out every additional battery dollar from your system? And then on the design side, we're pretty early in terms of how we understand how to design these systems. I'll just give you one really easy example, which may seem obvious, but it's still that kind of gives you an example of where we are. Most systems are designed because of efficiency losses and degradation, that they're oversized at year one so that it sort of maintains that level of available energy over the lifetime of the system. What we've decided to do is more of a topping up strategy. So we'll oversize it a little bit, and every 3 to 4 years we'll top it up, right? So it's an augmentation strategy. It may seem very obvious when you talk about it, but that's not how a lot of the systems are designed today. And those are some of the things that you can do that are relatively easy, that have a huge impact on the bottom line of the system over its lifetime.
My name is Conrad Oki. I'm from Novatech, a substation automation company. My question is for Ron. You were talking about diesel power plants in basically off-grid situations. I'm thinking of a $80 million paperweight we built in Afghanistan a couple years ago, instead of building distributed microhydro. In that IRR calculation of what energy storage does for a hybrid system, where in that spreadsheet is the risk of political instability, because these off-grid situations are often,
Yeah.
out there.
Well, yes, it's an interesting question. I won't spend a lot of time talking about forward operating bases and that kind of stuff that have their own challenges, although frankly there's a huge opportunity for microgrids in military bases right here at home as well. But I think the political question and dealing with the 1.4 billion people in the world who have no electricity, more than half of those people are in sub-Saharan Africa, and that's not exactly the easiest place to go operate to get things done. I still remember I've had conference calls with people. We're actually deploying a system into sub-Saharan Africa this summer, and they ask you questions like, well, how rugged is your battery? And I didn't think it was all that obvious a question, really, because I said, well, it's a 20-foot steel shipping container. You lock the doors, walk away, remote monitoring. What are you getting at? And they go, no, we mean really rugged, like if someone shot at it, And of course, the company is now headquartered here in Austin, Texas, but most of my team is in Montana. So if you have most of your team in Montana, and the question that comes across the speakerphone is, if you shot at it, then everyone in the room is going, well, it depends on what kind of load you have and what kind of calorie. Yeah, I'm surrounded by experts, and I'm kind of going, no, I really don't think that's the point, And then they started, well, what if someone wants to vandalize it and set it on fire and whatever? So there are a lot of opportunities in remote microgrids, but you need a system that is inherently pretty rugged. It won't hurt people, and it's not easy for people to hurt it. And B, you'd better have some answer on remote monitoring and not need a lot of O&M trips, or you're going to spend a lot of money keeping that asset up and running.
Thank you. We get time for one last question.
Thank you. Mike Cleary, I'm the Chief Operating Officer for AEMO, which is the air quad equivalent in Australia. The question I have is, when does the price point hit? But I would like to give some context around it. And I do thank the group, by the way, for the information, because it's been very, very helpful for me. In Australia, we've got a grid that has 22 million customers on it. It's about the same size as ERCOT. But I've got 1.6 million of those customers on solar PV, right? When they get storage, and they want storage because they're at about 27 cents a kilowatt at the moment, I'm not waiting on anything to penetrate the market. I'm waiting for when the price point hits, because they're going to want it and they're going to get it, which is going to make my distribution network my largest producer of electricity. We reckon that when they get this, when our customers get it, that they could be off the grid anything between 80 and 90% of the time. I don't know where it is. I don't know what it's doing. I can't forecast for it, and my distribution network's not built to manage it. So the kicker for me is, when does the price point hit when it becomes available to them, so that I, as a grid operator, can actually manage it?
Well, I think that if you look at utilities around the world, probably the ones that will make that math work last, other than specific cases in, say, PJM or certain demand charge avoidance for behind-the-meter people, are going to be in the U.S. I mean, power is generally more expensive or less reliable, or both, outside the U.S. I don't know about the particulars of Australia. What I do know from prior company lives, and you would know this very well also, is you can have some really long lines in Australia. So getting out to, what is the frequency and what is the voltage on some of those could actually drive some need for some ancillary services out on that edge of that grid network, other than just somebody wanting to become a microgrid and get off the grid altogether. But I mean, it sounds like you've got a pretty high cost of electricity now, so I would say your headaches probably start within 2 years, whereas in the U.S. I think they'd probably be more within like 4 or 5 years.
Those of you who actually were upstairs, I know it was a great session, but we had a good time down here, I think. And then we had the regular session, and I thank you all for your interest and your questions. And I'd love to thank this panel. What an interesting group of really intelligent people. Thank you all.